Good afternoon, everyone. Thanks for being here. And thanks to Pablo for the very kind introduction. You've really been digging into the ancient archives of my work, I can see. And it's also an honor to be the inaugural speaker for what sounds like a very exciting program at your university. So I've been a machine learning researcher for what is now a pretty long career. And so suffice to say, I've seen quite a bit of change along the way. When I started studying machine learning in graduate school in the late 1980s, machine learning was then an obscure corner of the then discredited larger field of artificial intelligence. Discredited because the main complaint about artificial intelligence is that it had overpromised in what it could do and that it didn't really work very well in practice. And if we flash forward several decades now, it seems that now people feel the main problem with artificial intelligence and machine learning is that they work perhaps too well. And so my good friend and colleague on the Penn faculty, Aaron Roth, and I recently wrote this book called The Ethical Algorithm. And our book is really, it's really what we consider a popular science book. It's one of these books that's trying to explain some area of scientific research to a general audience. And so what I want to do today is kind of give you an overview of what that research area it is and why it came to be. But I think, you don't even have to be a specialist in machine learning or a scientist of any kind to have realized that, especially in the last decade or so, the scope of AI and machine learning have expanded tremendously and very rapidly. So again, back in the ancient days when I was a graduate student, to the extent that there were applications of machine learning in the real world at all, it was usually to predict natural phenomena or collective behavior. So for example, machine learning might be used for things like weather prediction or for predicting the directional movement of the stock markets tomorrow. But the rise of the consumer internet and all of the data that we as individuals generated about ourselves, about our interests, our health, our fears, many things through our internet activity, made it possible for machine learning to become personalized, for machine learning to build predictive models that don't just predict things about some collective system like the weather or the stock market, but really make predictions about you that are surprisingly accurate. Okay. And there are many great things about that. There are many exciting things about this technology. There are many tremendous uses of it. But as machine learning has become used more and more for making individual predictions about people, and not just inconsequential decisions like what ads you see on Facebook, for example, but really consequential decisions like what criminal sentence you receive as a convicted criminal, whether you get into the college that you applied to, whether you receive the loan that you applied to. So these are not small decisions, and algorithms and machine learning specifically are being widely used to either entirely automate decisions like that or to strongly inform human beings that make those decisions. Okay. And and with this have come, not just abstract concerns, but real demonstrations of the harm that can come from this. And those harms include violations of privacy. They include bias or discrimination to different racial groups or by gender. And these problems, right, these aren't sort of little corner case problems that only scientists are worried about. These problems have received a great deal of concern and visibility in the general mainstream media. And so by now we have a number of excellent general audience books describing these problems. Perhaps the most famous of them is the book Weapons of Math Destruction by Cathy O'Neil, which systematically takes the reader through different domains like consumer lending, criminal justice, education, employment, et cetera, where algorithms are used at scale and often demonstrably result in what we might consider very unfair or discriminatory decision-making. Similarly, algorithms of oppression make similar observations and arguments in the domain of search engines, Data and Goliath points out the many, many ways that we have evolved collectively towards, what we might call a surveillance economy, where, many things are free to us, many great services are free to us in the monetary sense, but not in the sense of the privacy that we give up in terms of the data that we provide to these services. And so, so why did we think that another book was needed on this topic? Well, our book is different in a very deliberate way. And just to be clear here, my co-author Aaron and I, we admire these books and others that I'm not showing you here very much. And where we think those books are especially strong is in articulating what the problems are and demonstrating that they are real and that we should be worried about them. But where we felt that these books were lacking was when they get to, kind of solutions. And each one of these books and many others like them do, after articulating what the problems are for many chapters, have usually towards the end a section on solutions. What can we do about these problems? And where we were disappointed is that most of these books, say things like, well, we need better laws, we need better regulations, we need watchdog groups, we really need to keep an eye on these problems. And again, just to be clear, my co-author and I agree with all those statements. We do think that laws and regulations need to be rewritten with the algorithmic era in mind. But as kind of practicing researchers in machine learning and algorithms, we also kind of thought, well, if there's something that we don't like about the behavior of our models or our algorithms, we could think about changing the algorithms and models in the first place to not exhibit the kind of anti-social behaviors that we don't like, rather than waiting for the harms to occur and then litigating them in court, for example. And this would be easy for me. There wouldn't be a book to write about this if that was all I had to say, which is, well, we should design our algorithms better to avoid violations of privacy or discriminatory behavior. But depending on how you count, roughly the last decade or so, machine learning researchers and researchers in related areas have actually been working quite hard to design algorithms and to modify the principles of machine learning and artificial intelligence in ways that either mitigates or eliminates the various social problems that these types of books identify, okay? And so our book is less about the problems, which we think other authors have done a very good job of articulating, but about the solutions. And when I say solutions, I really mean scientific solutions. So if the way we normally do machine learning results in discriminatory models, we should think about changing the way we do machine learning in a systematic, scientific, principled way to eliminate those problems, or at least to control them. Similarly, if our neural networks are leaking people's sensitive data, we should think about training our neural networks in, again, a principled scientific way that avoids or controls those problems. And so the research agenda that I'm talking about and that our book is about embedding social values in algorithms. And what I mean by that is literally in, for instance, our Python code, there would be lines of code that would enforce fairness constraints or privacy constraints or explainability and interpretability constraints. And so, I'm not talking about some abstract exercise where we sit around and talk about, how we might do this in the future. I'm really talking about a scientific field that has really blossomed in the last 10 years and about which there's, quite a bit to say, at least enough to populate a short book. And the first observation I want to make about this research agenda before I spend the rest of my time kind of giving you just a flavor of what it looks like is that if, as I'm proposing, we really in our Python code somehow embed constraints that enforce fairness, privacy, or whatever, the first thing we're going to have to do is be incredibly precise about definitions. We're going to have to say exactly what we mean by fairness, because after all, if we're going to explain it to a computer through our Python code, it's really got to be, reduced to almost a mathematical formula, or at least something that can be expressed algorithmically in a programming language. And one observation I like to make at this point is that, nobody should make any mistake that, computer scientists and machine learning and AI researchers are very, very far from the first community of scholars to think hard about questions like what is fairness and what is privacy. So if we think about fairness, at least back to the ancient Greek philosophers, there was deep thinking about this topic. And in more modern times, legal scholars, economists, and many other academic disciplines have thought very carefully about different notions of fairness. And some of those actually have an echo in the more scientific literature that I'm going to tell you about today. But one thing that separates the agenda that I'm proposing from all of those previous efforts is that a moral philosopher thinking about fairness never had the need or the interest in being so precise about what they meant by fairness that you could write it down in Python. Okay. And in fact, in many ways, that kind of demand for that sort of rigor is counterproductive in many settings. So, there's a reason why bodies of laws in the West don't spell out, contracts in the United States. They're very, very detailed and too long already, but they still are very far from specifying exactly what should happen under all possible circumstances. Because the idea is that you leave the corner cases, as we would call them, to the courts, right? And you count on human judgment to kind of read between the lines and interpret what the law should have intended in such a case. But when you're putting things in Python code, there's no human being to kind of mediate if there's ambiguity in the definition. And the reason I'm going on about this a little bit is that, as I will give a couple of examples of, sometimes just the act, even though it's not the end goal to simply be precise, sometimes being as precise as I'm suggesting about definitions of things like fairness and privacy will reveal flaws in our intuitions about those notions that we weren't going to discover any other way. And I'm going to give two examples, one in privacy and one in fairness, where by being precise, by thinking hard about what we really mean, we can we can disentangle good definitions from bad definitions. And just to be clear, right, it's not enough to be precise, right? That's a necessary but not sufficient condition for the research agenda I'm proposing. And what I mean by that is it's possible for me to give definitions of privacy and fairness that are extremely precise, but are simply bad definitions. And I'm going to give you two examples. And unfortunately, those two examples are exactly the definitions that have been adopted into wide bodies of law and regulations in the West. Okay. But our book is basically arranged in chapters around different social values or norms. So there's a chapter on algorithmic privacy. There's a chapter on algorithmic fairness. We discuss accountability, interpretability, et cetera. And you'll notice I'm writing these words in kind of increasingly lighter shades of text. And that is meant to convey our subjective opinions on how mature each of these areas are. So in our view, the study of algorithmic privacy is the most well-developed of the topics that we discuss in the book. The study of algorithmic fairness is a bit further behind, but off to a very good start. Areas like accountability and interpretability are interesting and important, but we feel like they're much less mature in the sense that, in our subjective opinions as authors and researchers, we don't think that those areas have found the right definitions yet, right? So to us, the struggle there is really in formulating the right definition of something like, let's say, interpretability or explainability. Okay, so what I want to spend most of the rest of my time doing is just giving you two little case studies in this research agenda. One is around privacy, and the other one is around fairness. And then depending on how much time I've used, maybe I'll make some remarks about the other topics and sort of social norms that we consider in the book. So I first want to talk about data privacy, right? About the idea of starting with some data set or database and wanting to, create a private version of it or do a computation on it that results in a private output, okay? And to sort of approach this topic, I'm going to start by discussing what is by far and away the most prevalent notion of privacy in widespread use in practice, in industry, governments, and elsewhere, which is anonymization, okay? So at a high level, the idea of anonymization is that I should take my data set and somehow, modify it in a way that the individual data, the data belonging to specific individual citizens that is in my data set cannot be linked to those individual citizens, okay? So to give an example, at the top, I have kind of here a table representing a kind of a fake, very small toy medical record database. Maybe it's the database from the hospital of the University of Pennsylvania, just a mile or so away from here. And let's suppose that the hospital of the University of Pennsylvania has decided that it wants to take its medical record database and release an anonymized version of it to the world for the purposes of fostering scientific research. So they want to do a good thing. They want to share some version of their valuable medical record database with scientists around the world for, let's say, so that those other scientists can build predictive models for rare diseases, for example. So this is the kind of use of data that we want to allow in society. But of course, there are privacy concerns, okay? And so to address those privacy concerns, the hospital has anonymized the database. So what is what is involved in anonymization? So you can think of anonymization as basically giving you two different operations on the database. One of them is redaction, or deletion. So one of the things you can do is go to certain columns like the names of the individual medical records in the database, and you can just delete that column. You can just remove all the information from it. And then another operation is what we might call coarsening, where I don't remove the information entirely, but I reduce its resolution. So for instance, here, rather than giving age in exact years, like 57 years old, I'm grouping things into buckets of 10 years. So somebody is 60 to 70, or they're 50 to 60, et cetera. I'm keeping gender around. Zip code, which is, in the United States, the regional mail code that sort of, locates you fairly precisely within, let's say, a square mile. Maybe I feel like that's too intrusive. And so I've deleted the last 2 digits of zip code, but I've kept the first 3. And then I'm keeping around various medical information, like whether you're a smoker or not, and, what your current diagnosis is, okay? And so what's the idea behind anonymization? Well, the idea behind anonymization is if I do enough of these two operations, deletion and coarsening, that somebody coming to this database shouldn't be able to kind of reverse engineer the identity of any particular person's medical record in this database, okay? So for example, suppose I have a neighbor and her name is Rebecca, and I know that she's female, and I know she's 57 years old, and I know this because I'm friendly with her and she's my neighbor, okay? So I know 3 things about Rebecca. I know her name, I know her age, 57, and I know her gender. And if I come to this anonymized database and I look at the columns that correspond to what I know about Rebecca, which are name, age, and gender, well, names are deleted entirely. But then on the remaining 2 columns that I know the values of age and gender, there are exactly 2 rows that match what I know about Rebecca, and they're highlighted in red, right? There are these 2 rows in which, somebody who's 57 would fall into this bucket, and then I know that she's female. And so the idea behind anonymization is that now I, knowing what I know about Rebecca and looking at this anonymized data set, I have confusion, right? I'm unsure whether this is Rebecca's medical record or this is Rebecca's medical record, okay? And so there's, this is supposed to be somehow a reassuring privacy guarantee to you as an individual. And notice that already, even though, yes, I am uncertain which of these two rows corresponds to Rebecca, I already know that she's either HIV or has colitis, and she might consider that to be a violation of her privacy already. Now, of course, I might try to wish that problem away by saying, oh, well, look, in a real medical database, there would be thousands and thousands of medical records, not just a handful. And if I did enough of this redaction and deletion, redaction and coarsening, in a real anonymized medical data set, there might be 100 rows that match what I know about Rebecca, not just 2. And now I'm really confused. Okay, the problem is that even that doesn't work. Okay, and here's what gets to what the real problem with anonymization is, which is, suppose that there's another hospital, let's say Jefferson Hospital, also here in downtown Philadelphia, and they've also anonymized their database and released it in a similar way. Okay, and let's suppose I know, or maybe I just guess, that my neighbor Rebecca has also been a patient at not just the upper hospital, but also at Jefferson Hospital here at the bottom. Okay, and again, there's been anonymization in the Jefferson database here at the bottom, and now you can see that based on what I know about my neighbor, there are 3 rows that match what I know about my neighbors, these 3 ones in red. But now if I take the intersection of these 2 databases, I now uniquely know that my neighbor is HIV, because that's the only diagnosis that matches between the intersection of the red rows at the top and the red rows at the bottom. Okay, now you might think, oh, maybe there's still some way of fixing this up and patching it up and still making it into a useful definition of data privacy. I'm going to ask you to take my word for it. That kind of game of cat and mouse, where somebody observed a terrible flaw in anonymization methods, and then other researchers said, oh, well, here's a fix for that problem. That game went on for like a good 10 years at the beginning of this century, until basically it was realized that anonymization methods are thoroughly broken and discredited. And to put it in conceptual terms, the reason they're thoroughly broken and discredited is that they pretend like the data set in front of you is the only data set in the world now or in perpetuity. And if there was ever a time when that was true, it is certainly not now in the modern algorithmic era. And this kind of what we would call a linkage attack that I just described, where I take 2 databases which have each been independently, separately anonymized, and I might have confused. It might be that in the top data set there are 100 things that match what I know about my neighbor Rebecca, and 100 things in the bottom one. But then when I combine these 2 allegedly anonymized data sets, all privacy guarantees are completely eradicated. So this is the opposite of what a computer scientist would call graceful degradation. You fall off a cliff when you combine these 2 data sets. And there's a famous quote by the Harvard professor Cynthia Dwork that kind of summarizes what the situation with the anonymity techniques is. And her quote is, "Anonymized data isn't." And what she means by this is sort of twofold. She means that either you haven't done enough of this redaction and coarsening to give any real promise of privacy, and then your data is not anonymous at all, or you've done so much of it that your data isn't data anymore in the sense of being useful. Because of course, I could always achieve perfect privacy by simply entirely deleting every column of the data set, right? And then there's just nothing, okay? And so the basic, kind of learning of the first decade of the century was those are kind of your 2 options. If you really want to provide a privacy guarantee that's meaningful, you'll have to essentially not make, good use of data. Okay. So what's a better definition? And I'm going to kind of creep up on it in 2 steps. So here's an alternate here's another definition of privacy that's flawed in the opposite direction. So if I claim to you that anonymity is flawed in the sense that it really doesn't provide any privacy guarantees at all, I'm going to now describe another definition of privacy that errs in the direction of being too demanding, meaning that if we adopt this definition, we wouldn't be able to do useful things with data. Okay, so imagine it's like 1950, and imagine that you're a smoker in England in 1950. And by the way, if you were an English citizen in 1950, or for that matter, probably anywhere in the world, there was a very good chance that you were a smoker, right? Smoking was very prevalent at that time. There's no social or health stigma associated with it at all. It was seen as glamorous, and we didn't yet know about the strong link between smoking and lung cancer. That was the result of a series of papers written by the British physicians Richard Dahl and Bradford Hill, and this is showing the cover page of their first article on the topic. And what Dahl and Hill did is they asked every doctor in the UK whether they would allow their medical record to be used in a study to try to determine the causes or correlations with smoking, with lung cancer. Okay, and one of the very first things they discovered was this fact that was not known before, which was that smoking and lung cancer are highly correlated. Okay, so now what's the definition of privacy I have in mind? So here's a definition of privacy. Suppose that you were one of these physicians debating whether to allow your medical record to be included. And suppose I promised you, I want to do some analysis, like Dahl and Hill's analysis, let's say, or some other analysis on medical records, including yours. And suppose I tell you, look, I promise you that no harm whatsoever will come to you as a result of the analysis that I'm going to do. So in other words, when I say no harm whatsoever, you can tell me what it is that you're worried about. You can basically say you're worried that your medical record will get released to the world. You can say you're worried that you will start receiving ads on Facebook for unwanted medical devices. You can tell me that your greatest fear is that you start receiving robocalls on your cell phone at dinner time, whatever it is. And my promise to you is that the risk of whatever you're worried about happening to you as a result of my using your data in my analysis the increase in the risk of what you're worried about will be negligible. In other words, whatever it is you're worried about, my analysis on your private data will not increase that risk or the probability of that thing happening to you by very much or at all. Okay, so this is, I'm not going to make this precise. People have made it precise. You can, but it's basically what it sounds like. Whatever you're worried about, I promise you that that harm is not going to, that harm is not going to come to you as a result of my analysis. Well, if you think about it, right? Let's suppose you were a smoker and you submitted to this study. Well, real harm will have come to you as a result of this study, right? Because before the study, nobody knew about the correlation between smoking and lung cancer. After the study that used your medical record, the world does know that there's a link between smoking and lung cancer. And so now, in particular, your health insurance company might decide that you are at greater risk of having lung cancer, and they might decide to raise your premiums. Okay, so we can actually say that real financial harm came to you as a result of this study that included your data. Okay, and so we would have violated this no harm whatsoever because your insurance premiums got raised. Okay, well, okay, so first of all, notice that this definition of privacy is a very strong one. I'm promising you that nothing bad is going to happen to you as a result of my analysis, but it's too strong in the sense that it doesn't allow us to do things like discover the link between smoking and lung cancer. We can't we can't make use of data anymore. Okay, so so now I want to observe that there's an escape hatch here that leads us to what I argue is the right definition of privacy. in this no harm whatsoever definition of privacy, I compared two alternatives, right? One is the harm that would come to you if I didn't do this analysis at all, if like Dahl and Hill didn't do their study at all, and the world never learned about the link between smoking and lung cancer. And the other is the world in which they did the study, including your medical record, and the link between the smoking and lung cancer is discovered. Okay, so world A was don't do the study at all. World B was do the study, including your medical record. Okay, so here's an observation about that comparison, which is, it's not as if your medical record was the crucial piece of information that allows Dahl and Hill to find a link between smoking and lung cancer. Rather, the link between smoking and lung cancer is what I might call a fact about the world that can be discovered through any sufficiently large database of medical records, right? It wasn't like your medical record was important. They just needed a sufficiently large number of smokers, non-smokers, and the cancer diagnosis for each one of them to just compute this correlation. In other words, that correlation is a statistical fact about the world that can be derived from any sufficiently large data set, okay? And so this suggests a slight but crucial modification of this definition. Rather than comparing the world in which the study isn't done at all to the study in which it's done, including your medical record, I propose that we compare doing the study with your medical record and still doing the study, but without your medical record, okay? So this leads us to what's known as differential privacy, which was first proposed in 2005. And so here's a little cartoon illustrating differential privacy. So in differential privacy, we start with a bunch of people's private data. Let's say these are medical records, okay? And there's a bunch of them, and they're going to be fed as input to some algorithm or analysis, like the Dahl and Hill analysis, okay? And I've highlighted your medical record in red. And so the two situations we're going to compare are I run the algorithm with everybody's medical record used, let's say all N medical records used, including yours, and the algorithm gives me some output. And then I'm going to compare running the algorithm or analysis again using N-1 medical records where you are the -1, okay? And what I'm going to ask of the algorithm, and by the way, differential privacy is a property of an algorithm, not of data, and that's important, okay? So we're rather than anonymization, where we're trying to sort of say whether a data set has a property or not, in differential privacy, we talk about whether an algorithm or an analysis has a privacy property. And what we want of this algorithm is that whether we ran the algorithm with all N medical records as input or with N-1 medical records, where your, for instance, medical record is the missing one, or any other person's is the missing one, the difference in the output of the algorithm should be negligible. So what I mean by that is that a third party looking at this algorithm and trying to decide whether the input was all of the medical records or all of the medical records minus yours cannot do better than random guessing at determining which of those two situations we were in. So a third party gets to see the output of the algorithm and then has to guess, was your medical record one of the inputs or not? And differential privacy informally asks that this third party can't really do that better than random guessing. And so why is this kind of a very strong, I might even argue, ideal notion of privacy? Well, it's because if we take it as an axiom, and I strongly argue that we should, if we take it as an axiom that your privacy cannot possibly be violated by an algorithm that didn't even touch your private data, then what we're asking for is that even if the algorithm does touch your private data, somebody observing the output of the algorithm can't tell the difference between the world in which your data wasn't used and it was used. And if we basically think of your privacy as being preserved, if your data isn't even touched, then the computation using your data is also private, okay? And if I gave you the technical definition of differential privacy, you would see, interestingly, that achieving differential privacy requires randomization. It requires this algorithm to actually flip coins during the computation in order to achieve the guarantee. And so when I talk about the output of the algorithm, because the algorithm is a randomized algorithm, the output of the algorithm is also randomized. And so we should really talk about the output distribution of the algorithm. There's some space, possibly very, very large space of possible outputs of the algorithm, but the randomization of the algorithm induces a probability distribution over that output space. And what we really ask for is that the probability distribution of the algorithm's output when your medical record is included and when it's not included be negligibly different. And when I say negligibly different, importantly, differential privacy has a knob. It basically says how strong a privacy guarantee are you going to make? And that knob will, the more privacy you demand, the more noisy the results of the output will be. Okay, so let me demystify this a little bit. I know that this is a lot of abstraction for late in the afternoon. With what is, to my knowledge, the very first example of a differentially private algorithm. We might even more correctly call it a differentially private protocol. And one of the interesting things about this differentially private protocol is that the introduction of this differentially private protocol precedes the introduction of the definition of differential privacy by 40 years. Okay, so and you'll see why you didn't need the definition of differential privacy to see why this protocol is a clever idea. Okay, so I'm going to tell you about randomized response, which is a method proposed in the mid-60s in the social psychology literature. And it's a proposal for a way of surveying a large population on a question that might have an embarrassing or stigmatizing answer. So to give a very topical example, suppose I want to survey the citizens of Philadelphia on the question, have you deliberately violated social distancing guidelines during the pandemic? Okay. And we might think that, answering yes to this question, if that truthfully saying that you violated social distancing guidelines in the pandemic, you might feel embarrassed to admit that. Okay. And so if I just ask this question straight up and I go to people like on the street or I invite them to my internet site to answer this question, I might expect a massive underreporting of the yes positive answers. And so I couldn't use the data to form an accurate estimate of the true fraction of the population that has violated social distancing guidelines. Okay, so what randomized response proposes instead is the following. Rather than saying to you, have you violated social distancing guidelines? Answer me yes or no. I ask you to do the following. In the privacy of your own home, I ask you to flip a coin, okay? And if that coin comes up heads, which is the first branch here, if the coin comes up heads, then I want you to answer truthfully. If you're going to follow this protocol, if you flip the coin and it comes up heads, you're going to say yes or no honestly whether you violated social distancing guidelines. On the other hand, if the coin comes up tails, which happens with probability half, if we go down this bottom branch, then I just ask you to flip the coin a second time and use the outcome of the coin to answer. So if you flip the coin a second time and it comes up heads, then you're asked to answer yes, regardless of what your truth is, regardless of whether you violated social distancing guidelines or not. And if it comes up tails, you're asked to answer no, regardless of what your truth is. Okay, so this protocol has two very nice properties. Notice that, if I somehow confront you with a yes answer, you came to my anonymous website, you followed this protocol, but then I was doing IP address tracking. And I go to Pablo, for instance, and I say, Pablo, you answered yes, you violated social distancing guidelines. What's wrong with you? Aren't you a good citizen? Pablo can say, no. Of course, I haven't violated social distancing guidelines, but I followed your protocol, and the first coin came up tails, so I went down here, and the second one came up heads, so I answered yes. So notice that every single person who answers yes to this simultaneously has this plausible deniability. Anybody who answers yes can always say, I took this path through the protocol, and that's why I answered yes. And I can't really refute any of them. Okay, so everybody has a very strong notion of privacy here in the sense just of plausible deniability. On the other hand, a little bit of arithmetic will reveal that if a population of n individuals all honestly follows this protocol, that even though everybody who answers yes has plausible deniability, you can back out from the answers an estimate of the fraction of people who have violated social distancing guidelines that's accurate to within plus or minus 1 over square root of n. So this protocol has both very strong privacy properties, but it also is useful. But notice that it's useful in a very particular way. It is useful for estimating the percentage of the population that's violated social distancing guidelines, but it is completely useless for me attributing social distancing violation to any specific individual. And so this is like the balance that you want. You can do useful things like compute statistics and correlations, or even do machine learning, but you have very strong privacy guarantees, okay? And notice here that if I played around with the probabilities on this first branch, rather than asking you to answer truthfully with probability 1/2 and flip the coin again with probability 1/2, I could make the probability that we go to the top branch, I could make that some probability p, and the bottom branch would be 1 minus p. And notice that as I make p closer and closer to 1, I ask you, you're going up here with greater and greater probability, your privacy and plausibility deniability are going down, but the accuracy of my estimates is going up because there's less noise being added. On the other hand, if I make it more and more likely that we follow this branch, then your privacy guarantee gets stronger, but the noise in the data is greater also. And so I have less accurate answers. And in general, right, just to say something just one more detail about this, in general, in differential privacy, there's always a trade-off between 3 quantities: the amount of privacy you want, the accuracy of your computation, and the population size. So in general, for a fixed population size, or fixed number of inputs to the algorithm, there's a trade-off there's a tension between accuracy and privacy, but that trade-off can be made better and better by having a bigger and bigger data set size, okay? So in particular, you kind of can't really use differential privacy on super small data sets like 100 people. But if you have thousands or millions or tens of millions of records in your data set, then you can start to find you can basically provide strong privacy guarantees and get very accurate results simultaneously. Okay. So differential privacy is starting to see serious deployment in the field. So I'm going to try to speed up here a little bit so I have time to say a little bit about fairness. But in particular, here's a screenshot from back in the spring when Google started publishing community mobility reports. So Google used geolocation data from Android operating system phones to create what we might think of as heat maps of large metropolitan areas, basically showing you where large numbers of people were gathering too close to each other for too long, so that you might want to avoid those spots, or if you were one of the people gathering in those spots, you might want to stop doing that. But they knew that if they just did this in the straightforward way, it's possible that I could look at a series of these community mobility reports and figure out where you actually were each day at noon. Okay. And so rather than doing it in the straightforward way, they modified the way they computed these heat maps to incorporate differential privacy in order to both provide a useful heat map of where people were gathering in large numbers, but also give promises of individual privacy to people's geolocation data. The big moonshot for differential privacy is going on in the United States even as we speak, because the 2020 US Census, which basically counts citizens in the United States, and all kinds of other demographic information about them, not just, where you live, but how many people live in your household and what race and gender they are, and other kind of sensitive demographic information. They are going to release every report and statistic that's released from the raw underlying census data is going to be released under the constraint of differential privacy. And this is not without controversy, because as was pointed out in this New York Times opinion piece, this means that very, very small communities, which sometimes, for instance, in Alaska, might largely consist of Native Americans, might be so small that their numbers, after the noise is added to get differential privacy, they might essentially be entirely disappeared, okay? And the reason that this is controversial is because federal funding decisions, allocations are made based on census count reports. And so, what's going to happen to these small communities that are kind of wiped off the map when you add the noise to get differential privacy? There's not an easy answer to that question, because, as we argue in the book, whatever your notion of privacy is, privacy is in tension with accuracy, right? If I do things to numerical precision and release exact results without adding some kind of noise, you won't have any privacy. So if you want privacy, you're going to have to give up on accuracy, and accuracy often means, in industry, for instance, profitability or revenue or the like. And these are, science can't solve those problems. Science can articulate them and describe what the trade-offs we face are. Okay, I'm missing a slide here, but that's okay. So I want to talk now a little bit about algorithmic fairness, especially in the context of machine learning. So many of you have probably read mainstream media articles and maybe even scientific papers explaining how we often find that models trained on people's data will exhibit systematic bias by race or gender. So for instance, it's been noted that a number of commercially available face detection engines work demonstrably less well on Black women than they do on white men, okay? And one of the things we answer early on in the book is like, well, how does this happen in the first place? Is it because of incompetent scientists and engineers not implementing the principles of machine learning properly? Is it even worse because of racist scientists and engineers who are deliberately, changing the way we build models so as to do less well on Black women than white men? And, in our view and experience, the answer to those two questions is a resounding no. And in some ways, the real answer is worse, because the problem isn't with incompetent or racist modification of the principles of machine learning. It is with the principles of machine learning itself, okay? And so I'm going to just give a simple, again, toy but realistic example of why the standard principles of machine learning may indeed lead us to discriminatory behavior, but this also points the way to how we might algorithmically fix those problems. Okay, so in this toy example, let's suppose that the University of Pennsylvania, where I'm a faculty member, their undergraduate admissions office asks me to help them build a predictive model using high school applicants' data to Penn to predict whether a given applicant would succeed if they were admitted to Penn. Okay, and so what does the data look like? So the data is this green cloud of points, and I'm just going to give a two-dimensional example, but it's a pretty realistic one. And each green point here has an X value, which is the high school grade point average of the applicant, okay? And the Y value of the green points are the SAT scores of the high school applicants. So I don't know if you have something analogous to the SATs in Chile, but the SATs are standardized exams that high school seniors take that, you know, test you on reading, writing, mathematics, logic, things like this. And you know, sort of all high school seniors, or almost all high school seniors, would take these, and they would be used as one of the inputs to the college admissions process. Okay. And so here I'm just taking two things about your high school application: what your grades were in high school and what your standardized test scores were. And notice that each one of the green dots is either a plus or it's a minus. And the pluses indicate students that succeeded at the University of Pennsylvania, and the minuses indicate students that did not succeed. And for the definition of success, let's just take any objectively, quantifiably measurable outcome. So, you know, one example would be success means that you graduate from the university within 5 years of being admitted, and you have at least a B average in your grades. Okay, so this is, you know, when somebody finishes at Penn, we can see whether they met those two criteria, and that'll tell us whether they're a plus or minus. Now, notice that since I'm showing you data that already has pluses and minuses on it, it means that the data set that I have here in front of us is a data set that's already been filtered twice, right? Because in order to know whether somebody was a plus or minus at the University of Pennsylvania, first of all, they had to have applied. Then I guess there's three filters. They had to have applied, they had to be admitted, and then they had to have actually chosen to come, okay? But let's suppose that this is the historical data we have. These are actual students that were admitted in the past to Penn, they attended Penn, and we know whether they're pluses or minuses, okay? And this data set kind of looks like what you would expect. In general, the students that succeeded are up and to the right, higher GPA grades overall and higher standardized test score. The minuses tend to be towards the lower left, but it's noisy, right? You see some minuses way up here with high grades and high standardized test scores. Here's a plus down here with a much lower grades and much lower SAT score. And even if you don't have any experience in machine learning, and I asked you to look at this data set and build a good predictive model that we could apply to future applicants to try to guess whether they'd succeed or not, you might very well pick this blue linear classifier, right? This blue line does a pretty good job of separating from the pluses from the minuses. And so we could use it if in the future you gave me a point that was like here, I could say like, well, this person is above this blue line, let's accept them. And here, this is a student below that line, let's not accept them, okay? It's not perfect, right? As usual in machine learning, we have errors, right? So here's a couple of students that this model would have accepted who in fact did not succeed. And here's a couple of students that this model would have rejected that did in fact succeed. Okay, but it does a pretty good job, okay? And this is the standard principle of machine learning, right? You basically pick some class of models like linear separators, and you find the model that on your historical or training data makes the fewest mistakes possible, which in this case is this blue line. So now suppose, I'm losing my, hang on. Let me just quickly shift to a different deck. Sorry. I don't know why I lost slides, but okay. Yeah. All right. Okay. All right, so here we are. So now suppose I told you though, that this green data set was not the entire data set. There was another subpopulation of historical students. Let's call them the orange subpopulation. And here are their points. And there's a few things I want you to notice about the oranges. First of all, they are a minority population in the literal sense that there are far fewer orange points than there were green points. Secondly, there seems to be something systematically different about the distribution of the orange points than the green points. In particular, the standardized test scores of the orange points seems to be lower than the green points, right? The orange cloud seems kind of shifted down on the y-axis compared to the green cloud, okay? And we might wonder, why is this? And so I might tell you the following story. Suppose I told you that the green students were generally from wealthy families. And because they were from wealthy families, they had both the time and the money to pay for professional preparation courses for the standardized tests, and also for multiple retakes of the tests. So in the United States, on these standardized tests, there's an entire industry of tutors and classes you can take for money that will try to prepare you better for the exam. And you can also you can take the exam more than once, but taking it costs like $100 each time, okay? So the green population has the time and money to pay for these courses, take the exam multiple times, and then they get to send their best set of scores to the university, okay? The orange population, they're from less wealthy families. They can't afford this. Maybe they're working a job after school to help their family. So they do a bit of study for the exam on their own. They take it once and they take whatever score they get. Now, despite that fact, though, they are not less well prepared for college, right? So if you'd counted carefully in the green points, you would have discovered that slightly less than half of the greens were pluses. Here, the oranges are exactly 50-50. And if I ask you to build a good model for predicting success from just the orange points, you might pick this purple linear separator, which does a perfect job of separating pluses from minus. Now, the problem comes when we look at the combined data set. If we just apply the standard principle of machine learning and say, well, what is the linear model that does the best job of separating pluses from minuses? It's unfortunately exactly the same model that we would have chosen on the green population alone. And the reason for this is intuitively obvious. If I try to shift this blue line down far enough to accept these 5 orange pluses, I will pick up so many more green minuses along the way that my overall error rate would increase, okay? And so this model, which is the model that the vanilla principles of machine learning would select, it's the model that minimizes the overall error rate on the combined data set. We can also articulate now a quantitative sense in which it's unfair, right? Because if we think about the type 1 and type 2 errors, false positives, false negatives, we might argue that in college admissions, that the greatest injustice you can inflict on a high school applicant is false rejection. In other words, denying admission to a student who would have succeeded if they came to your college, okay? And so this model, which minimizes the overall error rate, is also maximally unfair in the sense that its false rejection rate on the green population is close to 0, and its false rejection rate on the orange population is 100%, okay? Now, you might say, well, this is kind of silly. Why don't I build a 2-part model, which says if you're from the green population, I'm going to apply the blue separate linear classifier, and if you're from the orange population, I'm going to apply the purple one. And now, not only will I have close to 0 false rejection rates on both populations, my overall accuracy would improve as well, okay? So once again, to the extent that we have laws that are explicit about what's meant by fairness in machine learning and statistical modeling, this kind of 2-part model is often legally forbidden. So for example, in consumer lending in the United States, since the 1970s, it has been against the law to use race as an input in lending decisions, okay? And I understand the well-intentioned motivation behind that, The idea is somehow by refusing to allow race as an input to an algorithm, it must be fair by race, right? Well, wrong. And this is a perfect example of why, right? Because by forbidding me from using race and forcing me to pick a single model for the entire population, and my following the standard natural principle of trying to minimize the overall error, by refusing to let me use race as an input, you actually guarantee harm to the very group that you thought you were protecting by refusing to let me use race, okay? And so in the book, we argue that a much better type of law or principle is to actually explicitly say what you want the model's output to do rather than restricting the inputs that it can use. So in other words, what we should do is we should change the scientific principles by which we train our models. Rather than simply saying minimize the overall error, period, we could instead say minimize the overall error subject to the false rejection rates between green and oranges having to be the same. Now, that might be a very strong constraint, but we can also relax it. We can introduce a parameter or a knob. So I could basically look at the family of constrained optimization problems that have the form, minimize the overall error, which is the normal principle of machine learning, but subject to the constraint that the false rejection rate between orange and green, for example, has to be within X%. And now X could be 0%, meaning they have to be identical false rejection rates, or I could relax it and allow it to be 1% or 5% or 10% or 25%. And of course, if I allow the false rejection rates to differ by 100% between the two populations, it's like I didn't ask for any fairness constraint at all. And armed with this new way of training models, you can actually trace out the frontier, the trade-off, if you like, or what an economist would call like the efficient or Pareto frontier between error and unfairness. So what I'm showing you here, let's just look at the figure on the left, is on a real data set where he's showing me something, but I'm not sure what. Oh, 3 minutes. Yeah. Okay, good. I think I'll make this my last slide and just leave some time for Q&A. So what I'm showing here on the left is on a real data set where fairness is a consideration, and we want to do something like approximately equalize, let's say, the false rejection rate across different racial groups. I'm showing you an empirically generated plot by an algorithm, which is, has this knob that lets us say, like, well, what is the allowed difference in false rejection rates across racial groups, okay? And each one of the red dots corresponds to a different model. So if you think back about the cloud of points on the last slide, each dot here corresponds to like a different linear classifier that we could draw through the cloud of points. And the x-axis for each dot is the error of that model overall, ignoring race. And the y value is the difference in false rejection rates across different racial groups for that same model. So if you like, the error is on the x-axis, the unfairness is on the y-axis, okay? We wish we could be at the origin. We wish we could find a model which has 0 error and 0 unfairness. But in any real machine learning application, we're not even going to get to 0 error, even ignoring fairness. And so you can see, we face a trade-off here. We could pick, for instance, this model up here. And this is basically the model that just uses the standard principles of machine learning and ignores fairness entirely. And as such, it has the lowest error, but the highest unfairness. At the other end of this curve is a model that has 0 unfairness at the expense of having much higher error. And in between, we get in between, okay? And in the book, we argue that this is kind of where science has to stop and policy has to start, but that visualizations like this are a very good interface between science and policy, right? Because I can show the Penn Admissions Office a curve like this, that quantifies the trade-off and choices that they have between their overall accuracy in admissions decisions and the discrimination that they're showing against, let's say, different racial or other subgroups. But, so I can do that. I'm a machine learning researcher. This is the kind of thing I do for a living. But I shouldn't also be the one that says, and I think we should pick this model for our admissions decisions, right? Hopefully somebody that has been thinking about college admissions and racial parity and gender parity in college admissions for much, much longer than I have would look at a curve like this and make the hard decision about where exactly to be on the curve, okay? And so with that, let me stop. Let me just, as a teaser or advertisement for the second half of the book, because what I've described today more or less covers the first half. In the second half of the book, we basically consider the ubiquitous settings in modern technological society, where, unlike the examples I've given for fairness and privacy, it's not simply about some algorithm operating on our data and we may not even know it, right? So I've given examples where, okay, an algorithm might have leaked your private data, or it might have unfairly treated you or your racial group. And you might not even know that this has happened. There's no interaction between you and this algorithm, other than you're perhaps being told what the decision of the algorithm was. There are many other settings in modern technological society where actually the algorithm, or more accurately, perhaps the app, is in a feedback loop with a population of users. And, the app is performing some valuable service on behalf of the users, but then it's collecting the user's data to modify the app, which then in turn modifies the behavior of individuals. So, a good example are navigation apps like Google Maps or Waze, right? Which are doing something very useful for us, right? They're basically taking where I am and where I want to go to, and they're using real-time traffic information from GPS devices to sort of, map out my shortest driving time route. But of course, we're influencing the app behavior, and it's kind of mediating what we might think of as a game, right? We're all players in this very complicated multi-party game, and it really is a game in the game theory sense, right? Because my driving on the roads inflicts what an economist would call a negative externality on you in the form of an incremental increase in traffic, okay? And so, something like Google Maps is essentially mediating this game on our behalf. And in the book, we similarly argue that, things like Facebook, the newsfeed algorithm of Facebook, is also doing something like Google Maps or Waze, in the sense that it's optimizing the contents that we see instead of the route that we drive on the roads. It's optimizing that content for our entertainment, or what's known as engagement in the industry. And in the second half of the book, we talk about the fact that even apps that seem to be straightforwardly optimizing something for each of us individually in a way that selfishly feels good to each of us can drive us to bad equilibria in the game theoretic sense. So, for example, we probably all at some level enjoy the fact that Facebook seems to know what kind of content we like to see, we find entertaining, and what kinds of opinions we agree with. And it shows us that stuff instead of content that we don't like or find disagreeable, or opinions that we find offensive. And at the beginning, this seemed like, who could possibly object to this? Who wants to see stuff that they don't like instead of stuff that they like? And, this is a bad equilibrium in the sense that many people have observed that one of the global side effects of this myopic self-optimization is that it's perhaps led us to a less tolerant, deliberative, democratic society, and also created platforms that are vulnerable to manipulation, for example. And so in the second half of the book, we talk about these sorts of problems and algorithmic solutions to them as well, which in fact do kind of benefit from kind of game theoretic frameworks. And so let me stop there and If there's time for any questions, I'm happy to take them.
Thanks very much, Michael, for this very enlightening talk. I have some questions here, which I think it might be interesting for you to take. Someone asks, like, whether this algorithm that you described for privacy, whether it has been implemented. And here comes the issue of human engineering, right? Like, people might get confused while carrying out this algorithm, no? And like, this is a complicated algorithm to measure what people think or want to say, no?
Yeah. So I don't know actually whether there have been like serious widespread deployments of randomized response. So I really know randomized response is an example of differential privacy rather than its intended original usage, which was to actually survey, large populations on potentially embarrassing questions. And notice that it is true that for the two things I said to be true, namely that everybody has strong privacy or plausible deniability, and you can still back out very accurate estimates of aggregate statistics, people need to follow the protocol, right? And so they need to both understand it and they need to trust it, right? Which may or may not always be the case. And so if some unknown fraction of the population decides not to follow the protocol, or they don't understand the protocol, so they're doing something different, then notice that still anybody that did follow the protocol will still have plausible deniability. So you as an individual following the protocol, your privacy is guaranteed, no matter what everybody else does, okay? But if I, as the researcher, want to be able to get accurate estimates of the fraction of violators of social distancing, I really need everybody to do it correctly. However, let me point out that things very similar to randomized response are actually used in practice, not by people, but by algorithms. So, for example, one of the first widespread deployments of differential privacy was on the Apple iOS operating system, the operating system that governs all devices. So, and this is maybe already 5 years old. So Apple was interested in gathering from iPhones usage statistics about apps. They wanted to know, and more importantly, they wanted to share with app developers on their platform statistics about what apps were the most popular. What was it, Angry Birds or whatever, right? But they also knew that we might consider this to be private information, right? That how many hours I'm using each app on my iPhone, I might not be that comfortable with sharing that data with Apple and all of its developers, okay? So what they did is they released a version of iOS, so they released an update of iOS that would transmit my app usage to, the mothership in Cupertino, California, but under differential privacy in a way that's very similar to randomized response. So what it does is it basically, periodically, let's say every week, it looks at how many hours I've used every app on my phone. And, it basically takes that bar chart or histogram, if you like, and it adds like a huge amount of noise to it. Like it really adds random numbers, random positive and negative numbers with zero mean to each one of my app usage statistics, okay? So, maybe I find it embarrassing that I still play Angry Birds 17 hours a week on my iPhone, but what the iOS is gonna do is on my phone, before the data ever leaves my phone, it's gonna add like, a random number between -50 and 50 hours to my Angry Birds usage. And so my 17 hours of Angry Birds usage this week might even become something nonsensical, like I played -2.5 hours of Angry Birds, okay? And so it's that noisy version of the app usage that gets sent to Cupertino. And so, at Apple headquarters, when they look at these noisy histograms, they basically can infer almost nothing about any one of our actual individual app usages. But when you have 500 million iPhone users and you average those histograms together, the noise cancels out, right? And this is what goes on in randomized response and in much of differential privacy. The noise at the aggregate, at the individual level, my histogram looks like pure garbage, pure noise. But at the aggregate level, when you average 500 million of these noisy histograms together, the noise cancels out and you get extremely accurate estimates of the collective averages, right, versus the individual histograms. And basically, to my knowledge, that is done on iOS to this day. And so this is an example of something very similar to randomized response, in the field, right? Instead of sort of asking questions like, have I violated social distancing? It's like, how many hours did I use this app? And if Apple confronts me, if Apple gets a number like, oh, I played 100 hours of Angry Birds, they know that, it's quite, they really don't know much about my true Angry Birds usage at all. And the noise cancels out at the collective level.
Juan, do we have time for one more question? Yes. So several questions have come out in the last minutes, and they are very difficult. So I don't have capacity to process them. And so let me take one that asks less on the side of your computer science work, but something that we are very much behind here in Chile is that what is the capacity of regulating these algorithms really from a legal point of view, no?
Yeah, okay, so this is a great topic. Let me say a few things about it. First of all, I count myself in the group of people that believe that we do need stronger laws and regulation around algorithmic decision-making, AI and machine learning. And in particular, algorithms are incredibly specific technological artifacts that do very specific technical things. And we can no longer regulate algorithms with vague laws and regulations, right? So if we're going to, if we're going to talk about trying to get algorithms that don't discriminate or are fair or are private, we need to say what those words mean. And even if you look at the bodies of law and regulation that people think are the strongest in this regard, they're really not at all, right? So I've read the GDPR from the EU, which people kind of hold up as this model of modern algorithmic regulation. And, there are some very specific things in that document, which I think, have teeth, as we would say, like the right to ask what data is being collected about you and asking the right for that data to be deleted or forgotten. But when it comes to things like privacy, fairness, bias, discrimination, you'll see those words all throughout the GDPR, and nowhere does it come even remotely close to saying what those words mean. And until you can tell, your regulatees what the words mean and what they're supposed to do, then there's a lot of inertia against doing anything at all. And I think that's the situation we're in right now. And at least in the United States, having spent a lot of time, working, on technology regulatory matters with, agencies like the Federal Communications Commission and the Department of Justice here, one big barrier I see to the change that I think needs to happen is that, unfortunately, I think these agencies are staffed with entirely the wrong kind of people. Okay. They're very smart people there. There are very quantitatively smart people at those agencies, but they tend to be from different backgrounds than is needed, right? So they tend to be, for instance, from economics background, right? So for instance, the Department of Justice in the United States is loaded with economists who study anti-monopoly models in particular, kind of antitrust things, okay? And they don't understand machine learning. And so they don't understand the technology companies they are regulating or what those companies do or what the science and engineering behind it is. And I think it's very hard to, even if we had more specific legislation and regulation, I think it'll be very hard to enforce it until there's also kind of a very different type of staffing at those agencies. I mean, basically, if you want to regulate the Googles and Facebooks of the world, you need to have some minimal fraction of your staff be people that are trained in the same way and the same sciences that the people that work at Facebook and Google have been trained in. And so I think that's going to take time. But I think it'll come. But I think the science is going to be ready sooner than society is ready to adopt it, just because of these, kind of social frictions.